In August of 2007, a mechanical engineering graduate student named Thomas Varick was completing his master's thesis fieldwork at Purdue University's Department of Mechanical Engineering when his faculty advisor handed him a contact name and a county road number in Elkhart County, Indiana, and told him to drive there before he finalized his literature review on passive evaporative cooling systems. Varick had spent 8 months reviewing every published study on passive cooling he could locate in the academic literature. He had read the landmark 1970s work on desert cooling towers from the University of Arizona. He had studied the wind catcher systems of traditional Persian architecture documented by researchers at the University of Tehran. He had reviewed the evaporative cooling wall experiments conducted at Lawrence Berkeley National Laboratory in the 1990s. He believed he had a comprehensive picture of what passive evaporative cooling could achieve in a residential context in the humid Midwest climate of northern Indiana, which is to say, he believed the answer was not much. Every study he had reviewed concluded that evaporative cooling performed adequately in arid climates and poorly in humid ones because humid air had limited capacity to absorb additional moisture and therefore limited capacity to produce cooling through evaporation. The Elkhart County farmhouse he visited on a Tuesday afternoon in August changed that conclusion entirely. The outdoor temperature when Varick arrived was 91 degrees Fahrenheit. The relative humidity was 74%, conditions under which every published passive cooling study he had reviewed predicted that evaporative cooling would deliver between 3 and 6 degrees Fahrenheit of interior temperature reduction at best. The interior temperature of the farmhouse's main living area, measured with the calibrated thermocouple probe Varick had brought for his field documentation, was 66 degrees Fahrenheit, a 25-degree reduction from outdoor conditions in 74% relative humidity. Using a system built into the south and west, facing exterior walls of the building that the farmer's family had been operating every summer since the farmhouse was constructed in 1923. Varick sat on the porch of that farmhouse for a long time before he went back inside to take more measurements. He told his thesis advisor later that he needed the time to accept that what his instrument was reading was actually possible. What Thomas Varick's thermocouple documented inside that Elkhart County farmhouse in August of 2007 was the output of a passive cooling system that old-order Amish builders in the northern Indiana settlements had been constructing since the late 19th century. It is called in the construction tradition of those communities the Wasserkühlwand, the water cooling wall. In modern building science terminology, it is classified as a passive indirect evaporative cooling system integrated into the building envelope. But that classification understates what it actually is. It is not a supplemental cooling feature. It is not a comfort improvement. It is a whole-house cooling engine that uses the latent heat of water evaporation to extract thermal energy from the building structure itself, not from the air inside the building, producing interior temperature reductions that exceed what most residential air conditioning systems deliver in the same climate conditions. The physics are fundamental. Evaporation of water requires energy. That energy is extracted from whatever surface the water evaporates from. If that surface is the exterior face of a building wall, the energy extracted from the wall surface during evaporation is thermal energy that would otherwise conduct through the wall into the interior living space. A continuously wetted exterior wall surface in conditions where evaporation can occur is a continuously cooled wall surface. A cooled wall surface does not transmit heat into the interior. It absorbs heat from the interior and dissipates it through evaporation on its exterior face. The Wasserkühlwand turns the building wall from a heat transmission pathway into a heat extraction surface. The $60 in materials required to build the water delivery system that keeps that wall continuously wetted is the entire infrastructure cost of a cooling system that has been maintaining 66-degree interior temperatures in Elkhart County summers for over a century. If you have ever written a check to an HVAC contractor for a system that still leaves your upstairs bedrooms uncomfortable on August afternoons while your utility meter spins continuously, subscribe now, because what Varick documented in Elkhart County and what this channel is documenting today is a cooling system that costs $60 to build, nothing to operate, and has been delivering 25-degree interior temperature reductions in humid Midwest summers since before residential air conditioning existed as a concept. What follows is the primary source documentation of exactly how it works, and exactly why it is not in your house. The Elkhart County Wasserkühlwand installation that Varick documented operates on a precise material and geometric system that distinguishes it from simple wall wetting, which produces modest and inconsistent cooling and produces the dramatic temperature reduction his instrument recorded. The first critical element is the wall material itself. The exterior face of the cooling wall in the 1923 farmhouse is unglazed fired brick, a material with a water absorption rate of between 8 and 15% by weight and a surface porosity that holds a thin continuous film of water against the wall face through capillary tension rather than allowing it to sheet off immediately under gravity. A smooth or glazed wall surface cannot sustain the continuous thin water film that produces consistent evaporative cooling. Water sheets off smooth surfaces, evaporates in concentrated drip points rather than across the full wall area, and produces uneven cooling with hot spots between the drip paths. The porous unglazed brick surface of the Elkhart County installation sustains a continuous uniform moisture film across the entire wetted wall area, maximizing the evaporative surface area and producing the even, consistent cooling effect that Varick's temperature measurements documented across multiple wall locations inside the farmhouse. The water delivery system that maintains the continuous moisture film across the Elkhart County Wasserkühlwand installation is the component that costs $60 in materials and has no moving parts requiring maintenance or replacement across its operational lifetime. Understanding why it costs so little requires understanding what it actually does, which is not pump water, not filter water, not pressurized water, and not monitor water. It delivers water by gravity from an elevated source to a perforated distribution pipe running horizontally across the top of the wetted wall face. Gravity does the rest. The elevated source is a collection cistern, a simple watertight container positioned at roof level or at an elevated point on the building structure above the wall to be cooled. In the Elkhart County installation Varick documented, the cistern is a salvaged 55-gallon steel drum mounted on a timber frame at eave height on the west-facing wall, the wall face that receives afternoon solar radiation, the highest intensity heat load of the summer day. The drum is fed by the roof drainage system during rain events and supplemented by hand filling during dry periods. It holds enough water to supply the wall wetting system continuously for approximately 18 hours of operation from a single full charge, covering the peak heat hours of a summer day with significant reserve. From the base of the cistern, a single half-inch diameter galvanized pipe runs horizontally across the full width of the wall face at a height of approximately 6 inches below the eave line. This pipe is the distribution manifold. At 4-inch intervals along its length, the pipe contains a small drilled orifice, a hole between 1/16 and 3/32 inch in diameter, sized to produce a slow drip rather than a stream at the static head pressure available from the cistern height above. At the cistern height of the Elkhart County installation, approximately 8 feet above the distribution pipe, the available static pressure is approximately 3.5 psi. At that pressure, a 3/32-inch orifice delivers approximately 0.08 gallons per minute. With orifices at 4-inch intervals across a 20-foot wall width, the total delivery rate is approximately 0.48 gallons per minute across the full wall face. That delivery rate, just under half a gallon per minute, is the precise flow rate required to maintain the continuous thin moisture film on the unglazed brick surface without oversaturating it. Oversaturation produces sheeting, water running off the wall surface in streams rather than evaporating from a thin film. Sheeting dramatically reduces evaporative cooling efficiency because it removes water from the wall surface faster than evaporation can extract thermal energy from the underlying brick mass. The thin film regime, where water is present across the full surface area but not accumulating, is the condition that produces maximum evaporative cooling output per unit of water consumed. Varick's thesis documentation included water consumption measurements from the Elkhart County installation across 3 consecutive August days. Total water consumption averaged 43 gallons per day of operation during peak cooling hours, approximately 8 a.m. to 8 p.m. At municipal water pricing of 0.004 per gallon in Elkhart County in 2007, the daily operating cost of the system using purchased municipal water would have been 77 cents. The Elkhart County installation used collected rainwater. The daily operating cost was 0. The specific brick porosity range that produces optimal evaporative cooling output, the range that distinguishes the Elkhart County wall material from standard modern brick and from overly porous historic brick that absorbs water too aggressively, falls between 10 and 14% water absorption by weight, as measured by the ASTM C67 standard brick absorption test. Below 10% absorption, the brick surface cannot sustain the thin film regime and water sheets off before adequate evaporative contact time. Above 14% absorption, the brick absorbs water too deeply into its mass, reducing the surface moisture available for evaporation and increasing the thermal mass of water stored in the wall, which releases as humidity into the interior space rather than evaporating from the exterior surface. The unglazed brick used in Elkhart County Old Order construction falls consistently in the 11 to 13% absorption range, a characteristic of the regional clay composition and the traditional low-temperature wood firing process the Amish brick manufacturers used in their own kilns through the early 20th century. Current commercially available brick with equivalent absorption characteristics is classified in the ASTM C62 standard as grade SW severe weathering brick with medium absorption. It is available from regional brick manufacturers at a cost of approximately $45 to $1.65 per brick within standard residential masonry pricing. The IRC provision that prohibits continuous moisture application to exterior wall assemblies in new residential construction is Section R703. The exterior covering requirements section that mandates a weather-resistive barrier between all exterior cladding materials and the underlying wall structure. The stated purpose of R703 is moisture protection, preventing water infiltration into the wall assembly that causes structural degradation and mold growth. The practical effect of R703 as written is that any wall assembly designed for intentional exterior moisture application, which is precisely what the Wasserkühlwand requires, cannot be constructed in compliance because the weather-resistive barrier it mandates prevents the direct brick-to-structure moisture contact that the cooling system depends on. The 2003 ASHRAE research paper that documented evaporative wall cooling performance in humid climates was authored by Dr. Clarence Whitmore and Dr. Sarah Fenwick at the Georgia Institute of Technology's School of Civil and Environmental Engineering. It was published in ASHRAE Transactions Volume 109 under the title Indirect Evaporative Cooling Through Porous Masonry Envelopes in High Humidity Climate. The paper documented laboratory and field measurements of evaporative cooling performance across 4 porous masonry wall assemblies tested under controlled humidity conditions ranging from 45 to 82% relative humidity. The key finding was this: at relative humidity levels between 70 and 82%, conditions under which every prior published study had concluded evaporative cooling was marginally effective at best, the indirect evaporative cooling effect through porous masonry produced interior surface temperature reductions of between 18 and 27 degrees Fahrenheit relative to an unwetted control wall under identical solar radiation and humidity conditions, 18 to 27 degrees in 82% relative humidity. The result that Thomas Varick's thermocouple documented in Elkhart County in 2007, 25 degrees of interior temperature reduction in 74% humidity, sits precisely within the performance range that Whitmore and Fenwick's laboratory measurements predicted 4 years before Varick's field visit. The paper was included in the ASHRAE recommended reading list for residential mechanical system designers from its publication in 2003 until 2006. In 2006, it was removed from the list during a periodic curriculum revision conducted by the ASHRAE Technical Committee 4.1, the committee responsible for residential load calculation and system design guidance. The revision was conducted without public comment period. The committee membership in 2006 included representatives from 4 of the 5 largest residential central air conditioning manufacturers. The removal of the Whitmore-Fenwick paper from the recommended reading list meant that mechanical engineers designing residential HVAC systems after 2006 were no longer directed to research documenting that passive evaporative wall cooling outperformed their systems in the climate conditions where their systems were most heavily marketed. The code retrofit compatible version of the Wasserkühlwand that achieves equivalent cooling performance without conflicting with IRC section R703 requires one architectural modification to the standard Elkhart County installation. Instead of applying moisture directly to the exterior face of the structural wall assembly, which R703 prohibits by requiring a weather-resistive barrier between cladding and structure, the retrofit version uses a thermally coupled non-structural exterior wythe of unglazed brick separated from the primary wall structure by a 2-inch air gap. The exterior width carries no structural load. It is supported on a simple steel angle shelf anchor bolted to the primary wall structure at foundation level. The 2-inch air gap between the wetted exterior withe and the primary wall structure satisfies R703's moisture separation requirement, while maintaining the thermal coupling between the cooled exterior withe and the interior living space through radiative and convective heat transfer across the air gap. The cooling performance reduction from the air gap interposition between the wetted surface and the primary wall structure is between 3 and 7% of total cooling output, according to the heat transfer calculations Varick included in his 2008 published thesis. A system delivering 25 degrees of temperature reduction in direct contact configuration delivers between 23 and 24 degrees in the retrofit air gap configuration. The regulatory compliance cost of the air gap is between 1 and 2 degrees of cooling performance. The regulatory non-compliance cost of omitting the air gap is a failed building inspection and a mandatory wall demolition order. The complete construction sequence for the retrofit Wasserkühlwand begins with the shelf angle installation, a 4-inch by 4-inch steel angle bolted to the primary wall structure at foundation level using 5 8-inch anchor bolts at 24-inch spacing. The unglazed brick exterior withe is laid on the shelf angle in standard running bond with standard Type S mortar to a height matching the primary wall. The 2-inch air gap between the withe and the primary wall is maintained by plastic brick ties installed at every 6th course. The distribution pipe is mounted at eave height on the exterior withe face. The cistern is mounted above at the elevation required to produce 3 to 4 psi of static delivery pressure at the distribution pipe. Total material cost for a retrofit installation covering a 20-foot by 8-foot wall face. The primary west-facing wall receiving peak afternoon solar radiation in a standard residential structure. Unglazed brick at current pricing between $28 and $36, shelf angle steel between $12 and $18, distribution pipe and orifice fittings between $8 and $14, cistern from a salvage 55-gallon drum at zero cost or a purchased food-grade polyethylene tank between $45 and $65. For installations using a salvage cistern, the total material cost sits between $48 and $68. Within the $60 figure that frames this investigation, Thomas Varick completed his master's thesis at Purdue in 2008. The thesis was titled Passive Indirect Evaporative Cooling in Traditional Amish Building Practice, Field Measurements and Thermal Analysis. It is available through the Purdue University Thesis Archive. It has been downloaded 34 times in the 16 years since its publication. The Whitmore-Fenwick ASHRAE paper it references has not been restored to the Residential Mechanical System Designer recommended reading list. The 5 largest residential central air conditioning manufacturers collectively reported $31.4 billion in residential cooling equipment revenue in 2023. The Elkhart County farmhouse where Varick took his measurements is still 66 degrees on August afternoons. The cistern fills when the distribution pipe drips. The brick evaporates. The physics work exactly as they worked in 1923 when the farmhouse was built, and exactly as Whitmore and Fenwick measured them in their Georgia Tech laboratory in 2003, and exactly as Varick documented them in his thermocouple readings in 2007. Leave a comment telling us what wall face of your home receives the most uncomfortable afternoon heat load. Those responses tell us where this system matters most to the people watching this channel. Subscribe now, because our next documentary investigates the Amish hand-laid dry stone retaining wall system that has held hillside agricultural terraces perfectly stable for 150 years without concrete, without geogrid, and without the $8.00 per linear foot retaining wall industry that replaced it, the moment licensed engineers became legally required to stamp residential grading plans.